Hi, today we will see an aircraft instrument. This is a transmitter receiver for radar altitude. Okay, so we can see that it was installed in an aircraft ZE458. I bought that thing from eBay UK for £25 exactly. So you can see that this thing is very well protected. This radar altimeter transmitter was manufactured by Thomson CSF. There are several connectors. It seems to be a BNC, a TNC. Okay. There is a main connector here. Okay, so there are two small coaxial connectors. There is here another coaxial connector and a test connector. Okay, look at that. Beautiful electronic boards. As you can see, there is a conformal coating on that board. There are several programmable parts. This one here and two other parts here. Microcontroller or maybe CPLD. This is the first board. 4 layers probably. No more than that. Okay. There are 6 layers actually. This is the crystal oscillator, 12 MHz. There is the voltage reference here, AD581. This is the comparator, LM111. There is another crystal oscillator, 16 MHz here. And this part, which is totally unknown, but a beautiful IC, a lot of pins. Okay, I cannot read the part number here. Okay, so this is the 68A02 microprocessor, 8 bits. So this is the 6840, so maybe a timer or something like that. And this should be the EEPROM. Actually, it's a flash memory, 29F something. Okay, so I can check this one. This is maybe a microcontroller. Actually it is a 68HC11. Yes, and this is another flash memory for the code. Can be tracing to perform a dump. Okay, of these two parts here. Very nice board. Let's see the second one here, which is also a beautiful one. Okay, so we have several logic ICs here. LS174, so I think this is a quad D flip-flop, maybe. All other parts are CMOS logic, CD something. Otherwise we have a 4081, we have a CD4024. It should be a counter. There is here a decimal counter, CD4017, quad NAND gate classic 4011. And here there is an AD55, an AD75, 41, so this should be a DAC. And here we have an analog section. Very beautiful construction. So the last one here seems to be the power supply, quite impressive. So you can see we have here 3 SG1524. This is the pulse width modulation controller. We have the 3 of them. 4 actually, didn't see this one. I didn't see there is another one here. Okay, so we have high temperature capacitors, 105 degrees. I cannot read the reference of this TO3 part here. I don't know if it is an IC or a transistor. On the other side, we have the RF section, probably. No, it is not an RF section, but we have here another analog board. There are several op-amps here, classic TL 080, 082, a lot of transistors here. Okay, so the RF section is probably inside the second shield here. Okay, so we need to remove that board first. Okay, so we can see here, this board can rotate here. Okay, so as you can see, so there are a lot of SFD parts on the bottom side of this board. Okay, and there is a strange part here. I don't know if it is a reader or something. Oh, this is the RF assembly, very beautiful thing. Okay, so this is exactly the microwave sub-assembly. We have here the meaning of the different sections. It is written in English and in French. Okay, so let's start by the linearization module. Okay, so this is a classic analog circuit. There is here a part SP8690. So this is maybe a prescaler, but I'm not sure. And we have here another SP8720. It can be maybe interesting to do the reverse engineering of that board. It is not complicated and we can learn something about that. So now let's see in details this microwave sub-assembly. Okay, I need to remove a lot of screws for that. Okay, look at that. This circuit is a preamplifier. Okay, so the output is here. Okay, and here we have the mixer. Here we can see these two diodes here. The input here is mixed with an oscillator here. Okay, so the circuit is the oscillator. Here we can see this strange arrangement. It seems to be an adjustment. And here the amplifier. A very beautiful design. So this is probably the input filter. Okay. Okay, so we can adjust here the bandpass filter using these 3 screws here, which permits to modify the capacitance. We can see here the output, a directional coupler. Okay, so there is a small diode here. Okay, and here we have DC voltage, okay, which is an image of the transmitted power. Let's see how this system works. We can see the aircraft here. There are 2 antennas here. One antenna for the transmitting signal and another one for the reception of the signal. The frequency transmitted is between 4.2 and 4.4 GHz. The carrier frequency is frequency modulated linearly. At a given moment, a frequency here is transmitted, and at the same time, another frequency is received. The difference of these 2 frequencies is proportional to the altitude here. The frequency modulation is used because it is much easier to measure a difference of frequency than a difference of time. This is why the delay is translated into a frequency variation. The measurement of the frequency difference is done using a mixer. When you multiply these 2 signals, you will have actually 2 different signals, one corresponding to the sum of the frequencies, and the second one corresponds to the difference of these 2 frequencies, and it is what we are looking for. So a simple mixer between the transmitted signal and the received one permits to have the frequency corresponding to the altitude. This is the block schematic of that system. It is a homodyne system. The received signal here is multiplied by a part of the transmitted signal. A low-pass filter permits to extract the difference of these 2 frequencies. This signal is fed to a frequency counter, which permits to compute the altitude. The VCO is used for the transmission. There is a frequency modulation using a triangle on that device. It seems that a sawtooth is used instead of a triangle. It is very important to have a very good linearity of the sweep here. On that device, a complex circuit is used in order to have a linear sweep, because the VCO, of course, is not linear. We can see here the complete schematic of the microwave assembly. The received antenna is here on the left. The antenna is connected to a passband input filter. We can see the physical construction of the filter here. The output of the filter is fed to a first isolator. The signal is fed to this preamplifier. So we can see this amplifier here. We can see this transistor. It is maybe a hybrid amplifier, I don't know. The output of the amplifier is fed to the mixer. The second input is here. It is the oscillator. The output is here. So this is the difference between the 2 frequencies. Okay, we can see the mixer here, and we can see the 2 diodes, D16 and D17. So this is the oscillator. The part of the output is fed to the mixer, and the second part is fed to another isolator here, to the down converter and the output amplifier after that. Okay, so you can see this hybrid coupler here, and the oscillator is constructed around this part. There is a trimmer capacitor here. So this is the down converter. The down converter permits to have a linear sweep. There is here an oscillator which seems to be a resonant cavity. You can see the cavity here. There is a screw which permits to adjust the local oscillator here. And this diode permits to provide a mixer between the output frequency here and the local oscillator. The difference of these 2 frequencies is approximately 100 MHz maximum. the signal is fed to this amplifier. The first stage uses this first transistor to N2222 in common emitter, and the second amplifier uses this transistor BSR14 in common base configuration. The output is on the collector here. The signal is fed to a divider 1280. The output is fed to a monostable which generates a pulse and a low pass filter. At the output here, there is the voltage, which is an image of the input frequency. The signal is compared to a sawtooth, okay, which is actually the sweep. The output is an error signal. This error signal is integrated and is fed to the VCO. So therefore, there will be an adjustment of the VCO in real time in order to have 0 at this input here. If we have 0, that means that we have also a perfect sawtooth is here, and therefore we have a linear output frequency here. So this is a control loop, and the frequency is controlled by this signal here. Okay, so I have done some calculations here, and we found that this difference is proportional to the altitude. The output signal here is fed to another isolator, okay, and this signal is fed to this amplifier. The output of the amplifier is fed to another isolator, and finally it is fed to a power management circuit. So we have on that line here 4 pin diodes. So this permits to adjust the power. You can see we have here a stub, and we have on that line a DC current, okay, which permits to modify the resistance of these diodes and therefore the output power. Okay, so we can see that this signal is fed to a small board, which is actually a voltage to current converter, and the voltage is connected to a DAC, which is on the CPU board. So therefore, the output power can be adjusted by firmware. There is also a measurement of the transmitted power using this directional coupler, which is here. So we can see the pin diodes here. The cathode of each diode is connected, okay, to the ground, and you can see the anodes here, which are connected to that line. Okay, we can see here the diode of the directional coupler. Okay, so we can see here another stub. The DC signal here is fed, okay, to the output here, which is the measurement of the output power, and the output is fed to the transmit antenna here. The directional coupler is connected to a comparator, but it is maybe connected also to an ADC. This is the linearization circuit, which permits to have a frequency proportional to an input voltage. The frequency of the signal, which is present at the output of the down converter here, is divided first by 4. After that, it is divided by 10, then by 32. At this output, there is a square wave with a frequency of 78 kHz, when the frequency at the input is 100 MHz. This signal is fed to this monostable, which is the classic 4028. This resistor is selected, so therefore at the output there is a rectangular signal, and the mean value of this rectangular signal is proportional to the input frequency. This signal here, this rectangular signal is fed to this second circuit. This is the summing point. The second input is this signal here, which is a negative ramp because of this negative amplifier here. The positive ramp is here. There is an adjustment of the gain. This signal is fed to this low-pass filter. It is fed to another filter, and there is also a rejection circuit which permits to reject a frequency of 12.5 MHz according to the values here of the capacitors and this inductor. This signal is fed to this integrator. This integrator is fed to another negative amplifier here with an adjustment of the gain, and the output is fed to the VCO. And we can see also that there is a direct path here between this amplifier and the negative ramp generator here. This permits to set the VCO with a nominal value, a kind of first order approximation. Therefore, the integrator works only with the second order signal, This permits to reduce the amplitude of the correction here. So therefore, this permits to reduce the setting time of this servo control loop. You can see the circuit board for this linearization circuit. This circuit is a part of the ramp generator. The main circuit is here in the middle. This is an integrator with this capacitor C33 in the feedback here. There is a JFET for the discharge of this capacitor. We can see that we can change the duration of the ramp using this MOSFET here, which permits to place R42 in parallel with R41. We can see that the grid of this JFET is connected to the output of this op-amp, which is used as a comparator. The JFET here is on when this voltage is positive. In that case, the grid is connected to ground, which is also the voltage of the source here. Actually, there is no specific source and drain. A JFET is totally symmetrical. Okay, you can exchange the source and drain. So therefore, if the grid is connected to ground, there is 0 volt here. Okay, and the JFET is equivalent to a resistor of 20 or 30 ohms approximately. So we can see that the output voltage is always positive, otherwise the voltage is clamped to minus 0.7 volt approximately because of this diode here. So therefore, when the voltage is positive enough, the output will go here to high level. Okay, so this permits to turn on this JFET and the capacitor is discharged. So this capacitor is a very good capacitor. It's a polypropylene capacitor